Hello everyone, and welcome to this edition of Numerical Analysis. We're going to talk about polynomial approximation. Specifically, we're going to talk about Taylor polynomial. I thought of making this video before making the video for solutions to equations in one variable because there is a concept that heavily ties to Taylor polynomial. So I thought you understanding this concept first would be actually ideal. So let's get into the video. So suppose you have a function f of x equals to e to the power x, and x is equal to 1. So naturally speaking, if you were to plug in 1 wherever x is, you're going to say f of x equals to Euler's constant to the power 1, of which you get your answer there, right? But now, what happens if you don't have x, but then we have been given a particular interval, a comma b, where a value x naught exists? Note to self that a comma b is an interval on the x-axis. So meaning we've been given a region within the x-axis where this function most likely lies. And then we've been given an initial value of x naught, right? How do we find the value of f of x equals to e to the power x? Well, that's where Taylor polynomial comes in. And it has the formula of f of x equals to the polynomial term Pn of x plus the remainder term Rn of x. So the whole idea or the concept here is when you add this polynomial term and the remainder term, you are going to get the exact value of f of x, right? So with that being said, let's get into the actual formula to finding Pn of x. So finding Pn of x is equal to the sum operator from k to n, right? So k to the number of times that we are required of f to the power k of x naught. So basically this is the derivative multiplied by x minus x naught to the power k divided by k factorial. And then we have the remainder term, which is equals to f, the derivative of k plus 1, so meaning the final value of k plus 1 of x naught multiplied by x minus x naught to the power k plus 1 divided by k plus 1 factorial. So we have this type of relationship between this guy and this guy. But to be able to expand on this term right here, we can just simply say Pn is equals to f of x naught plus f prime of x naught multiplied by x minus x naught, and so on and so forth, all the way up to n, as we can see there. So these are the formulas that you need for Taylor polynomials, and later on we'll discuss a little bit further on some more formulas that you might need, but this is the basic or the general idea that you're going to start with right now. Alright, so let's get into it. So let's just say, suppose that we don't know what x is, and we've been given an interval a comma b, where a value x naught exists. How do we find the value, right? So we say f of x is equal to e to the power x. So let k equal to 3. So let's just say we're finding the third Taylor polynomial, right? So meaning the highest value of this sum operator here, or this sum operator here, is going to be 3, right? So let k equal to 3. So we're going to start iterating from 0, 1, 2, and 3. Great. So we have our function here, but then what this statement actually means, we can go to P0, for which our first iteration there. We're going to say this is supposed to be x naught, so don't mind the typo. The first derivative of, sorry, not the first derivative, but the first iteration of x, because first derivative is just f prime there, so just imagine there's a 1 here. So if there's a 1, then this guy has a 0 there. So we just imagine that there's f0 of x naught multiplied by x minus x naught to the power 0. Remember, we're multiplying this, or we are raising it to the power of k. And if k is 0, then we get 0 factorial. And 0 factorial is 1, and anything raised to the power 0 is 1. So meaning this entire expression in the brackets here is 1, and this expression on the bottom is 1 as well. That's how we get this f of x naught, right? And then same goes with the first derivative here. We say p1 is going to p1 of x is going to be f of 1 of x naught multiplied by x minus x naught to the power 1, divided by 1 factorial. And anything divided by 1 is just the fraction itself. So that's how we actually derive all these um, values from, right? Okay, so you can do the same for the second derivative and third derivative. So when you let k equals to 3, you're basically saying find the third Taylor polynomial or whatnot. Not to self, I think I should tell you this before I forget later on in the video. Uh, there are two types of Taylor polynomials here. So there's the standard Taylor polynomial and you have the Maclaurin series. The Maclaurin series basically means that x naught is always 0. So meaning for the Maclaurin series, you are not necessarily given a point of x naught, right? So you are not given or you are not told what x naught actually is. So just a heads up, Maclaurin series means that x naught is equal to 0, right? Okay, now that that's off my chest, let's get into it. So because we're finding k here, so we're finding the third Taylor polynomial. So this guy always is gonna be there. We're always gonna find this guy is always gonna be there. But depending on what we are given as k, we could have maybe first Taylor polynomial, second Taylor polynomial, third Taylor polynomial, even fourth Taylor polynomial. So if they say first Taylor polynomial, they just mean find the first derivative of this polynomial, or that's where you end. Second, third, and fourth, and so on and so forth. So if they say let k equal to 3 for the third Taylor polynomial, then we're just simply saying find the third Taylor polynomial. We find f of the first derivative of x naught, the second derivative of x naught, the third derivative of x naught. So let's get into the problem solving. Okay, so we have that type of guy. So great, finding f1 of x, f2 of x, f3 of x. So we know that f of x is equals to Euler's constant to the power x, right? So meaning the first derivative using the formula of finding the derivative of this guy, we're just going to say it's e to the power x, right? Using a formula that I hope you wrote down in the calculus cheat sheets that I gave you. So using those formulas, we say e to the power x multiplied by 1 is equals to x, and the second derivative and third derivative, so on. We see that we have got e to the power x, e to the power x, and e to the power x, right? Great. So now, if x naught exists within the interval a comma b, then x naught equals to 0. Then let x be equal to x naught. So basically, if we've been given x naught value as 0, right? This is another Maclaurin series, so to say, because we have not been told to use a Maclaurin series, but we can be given that x naught is equal to 0. So if x naught is equal to 0 within the interval a comma b, then let x be equal to x naught. So if x equals to x naught, then we are just going to say replacing wherever there is x within the function with x naught, and if x naught equals to 0, then e to the power 0, any number raised to the power 0 is 1. So with f of x naught 1, f1 of x naught 1, f2 of x naught also 1, f3 of x naught is also equal to 1, and then we have our points. So we have our f of x naught, which is equal to 1. F of 1 is also equal to 1. Sorry, f prime of x naught is equal to 1. Second derivative of x naught is also equal to 1, and the third derivative of x naught is also going to be equal to 1, right? So punching this guy, getting into our formulas here, we're going to say these are our data points, and then if we were to replace or that in this function here, in this formula, we are going to say 1 for this guy here plus 1 multiplied by x, because our x naught is equal to 0 in this case, right? So if our x naught is equal to 0, then wherever in our formula there is x naught, we put 0 except for this guy, because we've already found these data points, right? So here we have a 0, there we have a 0, there we have a 0 as well. So basically we're just ignoring these terms. Great. So now we have f of x naught, which is equal to 1, and we have 1 there, plus this f prime of x naught is also equal to 1, so it's 1 multiplied by x, right? And we have this term here, plus 1, which is f, the second derivative of x naught, which is equal to 1 multiplied by x to the power 2 for this function here, divided by 2 factorial. 2 factorial is basically 2 by 1, which is just 2. And then we have this expression here, and 3 factorial, which is going to be 6. And then we have our polynomial there. Okay, great. So now, using this polynomial, let's just say suppose we're asked to approximate the value of the square root of Euler's constant using P3 of x. So meaning we have our polynomial, right, expression there. And then we say we use this expression to find this value. So we are going to say, first we're going to take this Euler's constant and make it into a more manageable function, right? So this is going to be Euler's constant to the power 0.5. And finding the x points for P3 of x, we're just going to say the x value of this guy here, the x value of e is equal to 0.5. So remember our function said that we have e to the power x, right? And then if that was the initial value or the initial function of f of x, so we've been told to say find or approximate the square root of e. So we did not know what x was initially, so we generated a polynomial to approximate what that value of x is. But still, we did not know what the x actually is. So now that we have replaced, or we have substituted, or we have simplified this expression into 1 over 2, which can also be simplified to 0.5, it means that our x value that we plug into this equation is 0.5 to find out the value of the square root of 2. Okay, so with that being said, e to the power x is equal to e to the power 1 over 2. Great. So now, if we were to cancel out the e values, x is going to equal to 1 over 2, as usual. So now, we are going to replace wherever x is within this polynomial equation, we're going to put in 0.5. And then once we do that, we have this type of scenario, and we have our answer 1.64833333. And I challenge you to use your calculator. Let me just use my calculator right now to prove if this equation is actually correct. And we say the square root of e is equal to 1.64721270, and so on and so forth. So we see that this value is very, very close to the actual value of the square root of Euler's number. So we can see that Taylor's polynomial is used for approximating values at a certain point and everything. So now let's look for the remainder term, right? But before we do that, here's a comparison where P3 of x is equal to 1.64583333, and the square root of e is equal to 1.68. So we see these two are very, very close when it comes to their values. Okay. So let's look at the remainder term, right? So knowing that k equal to 3, x not equal to 0, and x equals to 0.5, Let's find the remainder term of the square root of Euler's constant. Alright, so Rn of x is equal to the derivative term of k plus 1 of x naught multiplied by x minus x naught the power k plus 1 divided by k plus 1 factorial. So if our k is 3, our value here is going to be 4. If our x is 0.5, then wherever x is, we're going to put 0.5. And then wherever our x naught is 0, we're going to put a 0 there. But then we have our derivative of this guy here. So meaning we'll have to find e to the power x, the derivative, sorry, the fourth derivative of e to the power x. And we know that the fourth derivative of e to the power x is just simply 1, right? So here if we were to simplify the equation, we got 4 divided by 4 factorial, and then we have this type of relationship there. Great. So 4 factorial is equal to 24, and if we were to simplify this, the fourth derivative, sorry, of x naught is equal to 1. So meaning R3 of x is equal to 1 multiplied by x to the power 4 divided by 24. And if we were to plug in 0.5 wherever x is, we're going to get 0.5 to the power 4 divided by 24. And if you're good with your calculator, you will get something in this format here. This is your value. Great. So now, therefore, finding the actual value of the square root of e, we're going to add the polynomial term that we found plus the remainder term that we're just from finding, and then when you add this, it'll give you close, like very close to the actual value for when you find the square root of. So with that being said, let's actually go with the steps that we took answering this question. So we have step 1, where we have our formula here, right? This is very important, and you need to be able to understand this formula and to be able to grasp the concepts of it, right? So you got step 1, knowing the formula. Step 2, you find the derivatives of f of x, and then let f of x be equal to x naught. So find f of x, which is equal to e to the power x, and then like we did, so on and so forth, and then we just replace f of x with f of x naught, meaning wherever x was in this function, just plug in f of x naught, and in our case it was 0, so any number to the power 0 is 1, so all our values were 1. Okay, and then final step, step 3, which was evaluating Pn of x, and if needed by your lecturer or depending on the question, you find the remainder term and plugging in the values, and then you verify the terms if they actually do match your values. So basically, this is Taylor's polynomials, and that's just the gist of how to answer questions regarding Taylor polynomials. Remember, when your lecturer or the examiner asks you to say, find the Maclaurin series, x naught is automatically equal to 0. No ifs, but or maybes. Maclaurin, x naught equal to 0, and the normal Taylor series, x naught will be given to you. So that's basically everything to do with numerical analysis, polynomial approximation with Taylor's polynomials. I hope this video was enough to help you understand the concepts of Taylor's polynomials.